Identify the first mechanistic step in the reaction shown below. So if we take a look at the reaction that we have, we are starting with a terminal alkyne. And so this is called a terminal alkyne because it is at the end of the chain, which means that we have a hydrogen atom attached to that last sp hybridized carbon. And we can see that in the product, we have added an additional carbon. So we have added that methyl group in place of where the hydrogen was. And so what this tells us is that we are doing an alkylation reaction. And so specifically, we are alkylating the terminal alkyne. So if you want to find this in your textbook or look up more information, you would want to look up alkylation of terminal alkynes. So the very first thing that we're doing here is we're taking this terminal alkyne and we're reacting this with sodium amide. So whenever we see a sodium ion in front of something like this, we should recognize that this is how we write the general formula for a salt, where you have a cation and then an anion. So we want to recognize that this is sodium with a positive charge, which means that that NH2 must be NH2 minus. And so this is the conjugate base of ammonia. And so ammonia, if we remember from our earlier chapter on acids and bases, has a pKa of around 36. So that means that this NH2 minus is a very strong base. And also from that same chapter on acids and bases, we hopefully remember that a terminal alkyne is a very, very weak acid, but it is in fact a stronger acid than ammonia. So hopefully remember that the pKa for an alkyne, so let's draw the general structure for a terminal alkyne, is approximately 25. And so that means that when we take this terminal alkyne and the first thing we add is a strong base, we're going to have an acid-base reaction take place. So we've got this NH2 minus, and this can abstract this proton in a reaction that is going to favor products because this is our stronger acid, which means our equilibrium will go to form our weaker acid. Okay, so we will form from this step. Okay, and I don't have a whole lot of room here to write, so let's use the abbreviation that we often use for a benzene or phenyl ring, and that is pH. So I'm going to abbreviate that as pH so that I have some room to write it here. So this is going to form, that's our phenyl ring, this acetylide anion, and ammonia. And so because ammonia is a weaker base, that means that, or a weaker acid, I apologize, that means that this is also the weaker base. This is a favorable acid-base reaction, and that's the first step. And we were asked about the first step, so we can identify that now. And we should keep going though. Let's draw the final step as well. So once we form that acetylide ion, and in a second step, if we add in this alkyl halide, what we have now is a nucleophilic carbon and a carbon that is electrophilic with a partial positive charge. Right, so we've got a nucleophile and an electrophile, so they are going to react with each other. So this acetylide ion will form a new bond to that electrophilic carbon, and it's going to break the bond to the iodide. So that overall, we have added to our carbon chain. Right? And if you want to keep track of all species in the reaction, particularly when you're first learning these reactions, you might be saying to yourself, what happened to the sodium? What happened to the iodide? You're technically also forming sodium iodide in there, but as an inorganic byproduct, we often leave that out. Okay.